Hi everyone, this is part 2 of Calc 2 Lecture 14, which got cut off earlier today because the cameraman bumped the camera or something and it got shut off. It's kind of funny, it was the same day I was having trouble with cameras in my real analysis class, a different camera that didn't have any audio, and I had to redo that lecture entirely. But here I'm just doing the last 10 minutes or so of the Calc 2 Lecture 14b. What it was. And at the end of that lecture I had equations on the board involving taking parametric curves and dealing with the dx dt and dy dt, and ultimately this thing I called ds dt, which was the speed really, where s was the arc length, and trying to intuitively justify these equations non-rigorously, sort of as a scientist would approach it or as an engineer would approach it. We're not talking about Riemann sums here, we're sort of just talking about imagining small chunks. And I think the last thing I drew on the board here before the video went out was a parametric curve. And I zoomed in on a piece of the curve and said, hey, let's zoom in so far until it looks straight. And then we imagine drawing a right triangle, calling this side ds, this dx, and this dy. And ultimately, the equation that I had over on the right side of the board here was that ds was square root of dx squared plus dy squared by the Pythagorean theorem applied to these infinitesimally small quantities, which of course don't exist in the standard real number system, mathematically speaking, but we pretend they exist, scientists pretend they exist for the sake of intuition and trying to get to answers as soon as possible, though they do sometimes make mistakes when they use these things. It's easy to be confused by them and make mistakes, but they are kind of fun to use, I think. What I want to do here in the last 10 minutes or so is apply this idea to the context of polar coordinates and parametric curves that are created using polar coordinates. So I'm going to go ahead and use Mathematica now. And actually I'll write on the board as well, so I'll keep the screen up. I've got some Mathematica code that creates what I call a polar grid, and storing it in a variable that I call polar grid, and I can just retype that to see the polar grid. And in the class that I actually videotaped, I said, has anybody ever seen polar graph paper before? And about half the class raised their hands and said, yes, we've seen polar graph paper before. And that's what you kind of want to imagine this is. Though I've got the x and y axes in here as well. And first we got to discuss briefly what polar coordinates are. Hopefully you've had that in your pre-calculus class before. But if you haven't, this will be a brief introduction. Say you've got a point that happens to have rectangular coordinates, x equals 20, y equals 10. You're right here. There's a point whose rectangular coordinates are 20, 10. Can you see that okay? Zoom in if you need to there. That's good. What does that mean? It means that point is 20 units to the right of the y-axis along a perpendicular line to the y-axis, and 10 units above the x-axis along a perpendicular line up from the x-axis. That's not the only way to describe the location or address of this point. You can use polar coordinates. Polar coordinates specify two other quantities: the distance along a straight line from the origin to the point, call that r, and the angle that this line segment, or if you prefer thinking of it as a ray going on forever, makes with the positive x-axis. R can be found with the Pythagorean theorem. Draw a right triangle in here. This leg is size 20, this is size 10. This is going to be square root of 20 squared plus 10 squared, which will be square root of 500. Which, if you like, can be simplified to 10 is square root of 5. We'll have to think about how that's done if you don't remember. The angle can be found using trigonometry, SOHCAHTOA. TOA in particular, tangent of the angle is opposite over adjacent, so the angle can be calculated, since it is in the first quadrant, as the arc tangent of 10 over 20, which is the arc tangent of 1/2. Which, as far as I know, is not a simple angle in terms of pi radians, but You can certainly approximate it. I think it comes out to somewhere in the neighborhood of 0.4 radians or so, and 25 or 26 degrees or so is what the angle is. And you can check that somewhere in that ballpark is what this angle is. You could use the arc cosine or the arc sine function to find it. You also, well, first of all, you would represent the point in polar coordinates in this way then. You'd say r comma theta is 10 square root of 5 comma arc tangent of 1/2. Polar representations are not unique. You can add any integer multiple of 2 pi to this. 2 pi, 4 pi, 6 pi, 8 pi, negative 2 pi, negative 4 pi, negative 6 pi, indicating continuing to go around the horn there. And you get another representation of the exact same point, like this, etc. It turns out, though you don't always want to do this, sometimes, especially when you're making polar graphs, you might want to allow r to be negative. So I could use negative 10 root 5, but how can that be if r is a distance? Well, it can be if you consider the angle to be going the opposite direction, going all the way around to the opposite ray away from the origin. And then you'd have to do something different for the angle. You could do arctangent of 1/2 plus pi instead of 2 pi to get you to this angle here. Okay, it's just a different way of interpreting it. We don't always do that. It's most useful to think that way in the context of making polar graphs when you want to allow r to go negative to make some pretty graphs. Okay, but typically we have r be positive, and you can write an equation in general for r by using the Pythagorean theorem to be square root of x squared plus y squared. Does theta always equal the arctangent of y over x? Actually, no. And the tangent of theta actually doesn't always equal y over x either, though I will write that equation. If x is 0, this is not true. If the point is on the y-axis, you can't do this because you'd be dividing by 0. What do you do if x is 0? Well, you just got to look at the picture. If x is on the positive y-axis, then the angle is pi over 2, 90 degrees. If x is on the negative y-axis, then the angle, you take it to be 3 pi over 2, or negative pi over 2, 270 degrees, or negative 90 degrees, it doesn't matter. If you're at the origin, both x and y are 0, you can't use this equation. The origin, actually, theta can be anything. R is definitely 0 at the origin, but theta can be anything. The angle for the origin is anything, or you might say it's undefined. If you use the arctangent function to find theta in general, it only works as an arctangent of y over x if the point is in the first or fourth quadrant. If you're in the second or third quadrant, you have to add pi to it to get over it. Okay? So the point is, you got to look at the picture. If the point is in the second or third quadrant, you add pi to the arctangent of y over x to solve for theta. Going the other direction, if you know the polar coordinates and want to know the rectangular coordinates, you can use SOHCAHTOA to say that x is r cos theta and y is r sine theta. And there's no ambiguity there. Okay, you use those equations directly to find x and y. What I want to do in about 5 minutes now, we're going longer than 10 minutes here, is consider a polar graph and think about how you'd find distance traveled or arc length for the polar graph. What do I mean by a polar graph? I mean r, the r coordinate of the point, the distance to the origin depends on the angle theta of the point. You could replace r with f of theta. Like this. When you do that, you can get a graph in the plane, and you can think of these equations as parametric equations, giving you x and y as functions of theta instead of t. Theta is the angle, not time, though it actually doesn't hurt in some circumstances to pretend it's time, if that helps you understand the motion that you would see when you actually graph it. I will take the time to graph it for an example. We'll take a simple example, f of theta equals theta, and see what the graph looks like in Mathematica. plotting all the points in the plane whose polar coordinates really are equal to each other. Since r equals f of theta and f of theta is theta, the polar coordinates will be equal to each other. They have different units, measurement units. The theta would be in radians, the r would be in length units, meters or centimeters or whatever, but their numerical values would be the same. If I use show and put my polar plot in here, that gives the background, the polar grid. Actually, I guess it's called a polar grid, isn't it? Polar grid, yep, polar grid. And if I do polar plot, two capital P's in here, and plot the function theta, you can go past 2 pi here, and it's useful to do so to see a fuller picture of this. We will see a polar plot. What's going on here? At every point on this spiral, the r coordinate and the theta coordinate have the same numerical value. So as theta varies, starts at 0, r is 0, and as theta goes up to 2 pi, r is 2 pi. Look how far this is from the origin. Maybe zoom in if you need to. Here, there's 10 right there. 2, 4, 6, that's about 6.28 pi, 2 pi. Keep going around to 4 pi. 4 pi is about, what, 12.56. There's 10, there's 12. This is about 12.56 right there for the distance to the origin. This is doing what I said. What's the arc length of that? Well, again, you could imagine theta to be time if you wanted to. And so if you do imagine theta to be time, you could even consider the speed as a function of theta, if you like. Okay, this is all just however you want to think about it. You can imagine theta's time and an angle as well. And as usual, it'll be the square root of dx d theta squared plus dy d theta squared. The square root of the sum of the squares of the derivatives of these two things. That's how the book writes it. Theta is your parameter. So this is nothing more than the same equation we've written before, except we used t instead of theta. However, you do need to be careful here with the notation I've used. X does not equal f of theta. It equals f of theta times cosine theta. And there is no g of theta. Or if you prefer, g of theta is f of theta times sine theta. When you differentiate these things, when you find dx d theta and dy d theta, you've got to use the product rule. The cosines and the sines are going to come into play. It is the case that you get some simplification typically with the fact that cos squared theta plus sine squared theta equals 1. But if I'm going to write it based on that, I could also write it this way: the square root of d theta of f theta cos theta. That derivative gets squared plus d theta of f of theta sine theta. That derivative's got to get squared using the product rule in each of these derivatives. So you can imagine it could conceivably be kind of messy. And then the integral could be hard to do as well. Okay? Let me end by just saying that an interesting thing about this is if you are letting theta increase at a constant rate, which you would be doing if I made a manipulate here to animate this graph, which you can do on your own. I'm not going to take the time right now. You'd see the angle changing at a constant rate. However, because the object's getting further and further from the origin, the speed, thinking of theta as time, would keep increasing for sure. Okay? As theta goes at a constant rate, the spiral is going away from the origin, so the actual speed would be an increasing function of theta. And I'll end lecture 14B, part 2 right there.